next one that was on that page. It says, draw the Lewis structure for the disulfur monoxide molecule, S2O molecule. Be sure to include all resonance structures that satisfy the octet rule. Okay, well, first off, we have to realize how many valence electrons we have in this problem. In order to do that, we have to look at our periodic table and see how many valence electrons each element brings to the table. We know that all three of these atoms actually are going to bring 6. So 6 of them times 3 is 18 valence electrons. Perfect. Now we would ask ourselves, well, what is the central atom that would be the least electronegative? Now, in this case, it's not going to be the odd one out, like usual. Here, actually, sulfur is going to be the central atom. So if sulfur is a central atom, that means we have a sulfur and an oxygen that are both attached to that central sulfur in some way. We start out by drawing in single bonds, and if we draw single bonds, we see we've only used 4 electrons so far. And now we see if we wanted to, we could fill in octets. So if we fill in an octet here, and an octet here, now we notice something kind of strange. So we've already used 16 electrons, and we have nowhere else to put. If we put 2 electrons on that central sulfur would not be happy and it would not have an octet. So we must have another way to incorporate some electrons. Now, that usually means we have another type of bond. So, I'm going to erase those 2 electrons, and I'm going to create a double bond between the central sulfur and the sulfur on the left. If we do this, we now realize how many electrons do we have and how many do we need to use. Well, if we count, we have 2, 4, 6, 8, 10, 12, 14, 16, and we realize that the sulfur in the center is missing 2 electrons, so we draw in a lone pair on that central sulfur, and we realize now it has an octet, and we've used 18 valence electrons. And our question is, oh, is this the correct molecule? Is this neutral? Yes, it is, because if we calculated the charge on each of these elements, we would calculate the charge on sulfur from, it would be 6 minus, because 6 valence electrons to start with, minus the amount of bonds, so 2 bonds, minus the electrons found in lone pairs, which is 4, equals 0. Now for the central sulfur, it's 6 minus 3 minus 2, which is positive 1, so the central sulfur is positive 1 charge. And you might say, oh no, that doesn't seem right, but if we look at the last one, oxygen started with 6, has 1 bond, and also has 6 electrons in lone pairs. So that ends up being a negative 1 charge, and your overall structure is neutral. So this is the correct structure, and there are no resonance structures. I'm going to erase this problem now, and we're going to move on to the next page that you sent, and the next problem. So this next problem starts out by saying, for which of the following substances is required to convert 1 mole of the solid into separate ions? So this problem involves something that has to do with lattice energy. So lattice energy is the energy that is held between the bonds in an ionic compound. And these are all ionic compounds because they contain a metal and a non-metal. That's how you know that these are ionic compounds. So the question then becomes, well, which ones would be the kind of compounds that you were looking for to find your answer? Well, when we're looking at these compounds, let's find out what charge they each make in an ion. So if we look at the first one, A, magnesium oxide. Magnesium makes a +2 charge. Oxygen makes a -2 charge. Strontium makes a +2 charge. Oxygen again makes a -2 charge. Potassium makes a +1. Fluorine makes a -1. Cesium, +1. Fluorine again, -1. And lastly, magnesium, +2, and fluorine makes a -1. Now, we see that there are some similarities and differences between each of these parts of this problem. But one thing that we need to keep in mind is that for lattice energy, the smaller the charge, the smaller the lattice energy. So if we have a smaller charge, that means it's going to take less energy to break it or to convert it into its separate ions. So in order to answer this question, we're looking for ones that aren't so strong. So anything with a 2 charge, a charge of positive and negative 2, would be out as a choice. So the first one is out as a choice, the second one is out, and the last one is out, because all 3 of those contain plus 2s or minus 2s, or both. Now we have 2 remaining, K plus and cesium plus, and fluorine as the other element. So fluorine is the anion in both of these choices. And now our question becomes, well, how do we tell the difference between the 2 of them? Because potassium and cesium are both in the same period of the periodic table. So the question is, which one is the answer? Well, the cation with the biggest radius has the lowest lattice energy. So whichever one's bigger has a greater distance between its ions. So that means it has the lower lattice energy. So whichever one of these is bigger is the one you're looking for. Between cesium and potassium, obviously, because fluorine is the same in both of them. If you look at your periodic table, you find that cesium is much larger than potassium. It's 2 spots lower than it on the periodic table. So that's great. That means we know our answer. Our answer is cesium fluoride. So it's CSF is your answer, so it's choice D. Alright, now we're going to erase the board, and we're going to move on to the next problem. Okay, this problem says, draw a plausible Lewis structure for nitrogen trifluoride. Well, nitrogen trifluoride is NF3. NF3 is, well, in order to do this Lewis structure, we have to figure out what each atom brings to the table. In order to do that, we have to look at our periodic table. Our periodic table tells us that nitrogen has 5 valence electrons, and each fluorine brings in 7 valence electrons. So that's 7 times 3 is 21, plus 5 is 26. So we have 26 valence electrons, and we need to draw a structure. So, put nitrogen as the central atom, because nitrogen is the least electronegative. Then fill in the octets on the outer atoms. And if we do that, we notice that we're missing 2 electrons, and those 2 electrons are found on nitrogen, because everything wants an octet. And there we go. Now if we count, we realize we have 26 valence electrons, and this is our perfect structure. So this is the ideal Lewis structure for nitrogen trifluoride. Now we look at parts B, C, and D of this question. Part B says, what is the molecular geometry of NF3? So if we want to know the molecular geometry, we notice that we have 1 lone pair. So I know we have a chart for this in our book. We have 1 lone pair, and we have 3 bonded atoms to the center. So that is important to note. If you look in your table, you'll be able to see that the choice, when you have 3 bonded atoms and 1 lone pair, is a trigonal pyramidal. That is the name of the shape. Trigonal pyramidal. And the F and F bond angle, so all the bond angles in a trigonal pyramidal are 102.5 degrees. Okay, and the last question for that part says, does this molecule have a molecular dipole moment? So a dipole moment means, are electrons being pulled more in one direction of the molecule than in another? And the answer is yes. So electrons are being pulled this way, and this way, because fluorine is more electronegative than nitrogen. And overall, the dipole moment is leaving the nitrogen end more positive, and the end with all the fluorines more negative. So that is the answer to this problem. Okay, I'm now going to erase and move on to the next problem.